So welcome everyone. Thanks once again for being here for this seminar by Sebastian Bahamonde. Sebastian studied in Chile, in Concepcion. He did his bachelor and master there. He later he moved to the UK to do his PhD with Christian Bomer at UCL. And since then, he has worked in several places, among which is Tartu in Estonia, Tokyo Tech with Masahide Yamaguchi, and now he's in Kavli IPMU in Tokyo. And today he's going to talk about Metric-Affine theories of gravity and their applications. So yeah, Sebastian, the floor is yours.
Thank you very much, Costas, for the introduction. And this presentation is based on different papers. So some of these papers I will briefly mention in one line, probably. So, and the majority of these works have been in collaboration with also with Costa, Jackson, Jorge Gigante as well, and many people from Tartu as well. So this is more or less some application to metric-affine gravity, which is a modified theory of gravity that, in my opinion, is very interesting. So let's start with the basic. I will assume that you are not familiar with this concept. So I will first introduce what is the metric-affine geometry in general and with some motivations, why it's interesting. I will talk about teleparallel theories that probably you have noticed on arXiv every day that there are a lot of papers about teleparallel with the name teleparallel. So I will talk about the different versions. Let's say the standard version is with torsion and then with nonmetricity. This is called symmetric. Then I will jump to the more general scenarios. We have the gauge approach of gravity. And within this gauge approach of gravity, we have all the possible geometry, let's say, all the possible important quantities in geometry. And then I will introduce some recent words that we have developing related to applications to this metric-affine gravity, like cosmological perturbation in these theories. That is extremely complicated, let's say, I will say. And then I will talk about some issues related to the gauge approach and how it's possible to solve this issue by introducing some new approach, which is this cubic and extensions of gauge approach. And I will briefly mention our last application to metric-affine gravity that is related to algebraic classification of these models, let's say. Okay, let's start with definitions and conventions. So the idea is that in metric-affine geometries are related to a particular geometry where we don't live anymore in the Riemannian setting. So we don't have the Levi-Civita connection. We have a more general connection. In general, we have all the components, 96 components of the connection. 64, sorry, components of the connection. So in this case, we have the curvature tensor. Similarly as in the case of the Riemannian case, now we have this tilde on top. This tilde means is the general connection, the same definition, but now with the general connection. This is from the geometry point of view. This quantity also the same as in general relativity, for example. What it measures the change of vector components when we parallel transport along an infinitesimal closed curve. So in this case, for example, this schematic figure show this. When you start with this vector 1 and you want to come back, let's say, across this loop, in the end you notice that if you are in a manifold with curvature, you have something that is not in the same position, the vector. And this difference is related to the curvature tensor. And in general, we have 96 components, independent components in the general case, much more than in the standard Riemannian case, of course. After this, also we can have another object that is known as torsion tensor. Torsion tensor usually is 0 in GR, for example. And this is related to the antisymmetric part of the connection, defined like this. And geometrically speaking, this is related to, like, as this figure shows, as the non-closure of the infinitesimal parallelograms. So if you are in a geometry with torsion, this means that it's not possible to close this parallelogram when you try to do it in this way. So, and this difference is proportional to the so-called torsion tensor, that is the antisymmetric part of the connection. And in general, it contains 24 independent components. Have 24 components related to this object. And finally, we have another object that is called nonmetricity, That is the definition of just covariant derivative of the metric. This, of course, is equal to 0 in GR, because this is called the compatibility condition. But here, this is non-zero. And geometrically speaking, this guy measures, this figure represents when you try to parallel transport a vector. Now you change the norm of this vector. And actually, this figure is incomplete because also not only the norm can change, but also the angle. So when you parallel transport this vector, both the length or the norm of the vector and also the angle will change, and this is proportional to the so-called non-metricity tensor. And in general, in 4 dimensions, we have that this contains 40 independent components. So these are the 3 building blocks, let's say, of this geometric setting. It's called metric-affine gravity, and in these settings, the metric and the connection are independent. It's not like in GR where you have the Levi-Civita connection and all is encoded just in the metric. No, here we have more degrees of freedom, and they are encoded in the connection, and the connection is split into this torsion part and also this non-metricity part as new components. Okay, so we can use the so-called fundamental theory of Riemannian geometry in the absence of torsion non-metricity that says that we just have if the curvature is just the standard one, just the Levi-Civita tensor. I mean, computed just with the Levi-Civita tensor, Levi-Civita connection. However, in general, as I said before, you can decompose this guy when you have torsion and non-metricity with this tensor n. Here, this tensor n it's just a linear combination of torsion T and non-metricity Q. So this is the new degrees of freedom, and then you can write down the general curvature as the Levi-Civita part plus some corrections that are related to this tensor n. So this essentially are the new part related to this kind of geometries. Up to here, this is just geometry. It's just, I haven't introduced any theory of gravity. It's just purely geometrical identities, let's say. So, but these are very useful, let's say, to construct theories of gravity with this dynamical degrees of freedom. So, okay, so let's take a look at some properties of this curvature now. Now we only have one symmetry. The symmetry of the 2 indices, let's say, is antisymmetric in the last 2 indices. This is the only symmetry that we have in curvature. Recall you that for the Riemannian case, we have more symmetries because we know that we have just 20 degrees of freedom in that case, and here we have 96 degrees of freedom. Also, what is modified is the Bianchi identities. The Bianchi identities now, if you remember the Bianchi identities from your GR course, it says that the antisymmetric part of the curvature is equal to 0. So this part here, the right-hand side of this equation is identically 0. This is called the Bianchi identity when you have without the tilde. But now since you have more things, now the Bianchi identities are modified. And not only this, but also you have 2 extra Bianchi identities that are identically 0, let's say, in the Riemannian case. And these identities are important when you want to construct theories with dynamical, for example, torsion, because as you notice here, you have some kind of, if you put this R square, for example, automatically you will have some kind of derivative of torsion, and this will, for example, create some kinetic term for torsion. The same for non-metricity here. If you put this square, the symmetric part of the curvature square, you will automatically introduce some kinetic term for this field for non-metricity. So that's why it's important to understand this from the Bianchi identities. Then in GR, you can only formulate one contraction that is independent, the Ricci tensor. But here you can actually formulate 3 different independent rank 2 tensors. The first one is the Ricci, just with exactly as in the Riemannian case when you construct the third index with the fourth. But then you have the so-called Corricci with this hat on top that I will put. So this is other contraction that in the Riemannian case is just a linear combination. But this in general, in the Metric-Affine gravity is a different trace. And finally, we have also the last trace that is the first index with the last one, with the first 2 indices, sorry. And this is related to the so-called non-metricity and more important, the bile part of non-metricity, one particular part of the non-metricity. So this is also a kinetic term, let's say, if you put it a square. And then there is a unique scalar that you can construct. So if you put this construction with the metric here, there's only one unique independent scalar that is just the Ricci scalar. This one. This one is the same if you contract with any of these these two ones. Then there is also this pseudo scalar that is also, let's say, possible to construct that is different from zero. So this, as I said before, is just some notation, let's say, to understand the idea. And then let's try to particularly go to a particular case, to the so-called teleparallel gravity. Teleparallel gravity is a particular kind of setting where everything is a little bit simpler because the general metric-affine gravity is more complicated. But in this particular setting, one assumes by hand, let's say, that the full curvature, not the Levi-Civita one, not the Riemannian one, but the full curvature is equal to zero. So you say this is the so-called teleparallel condition. And then if you, for example, construct this guy with like to construct this Ricci scalar, you find this very nice relationship between the Ricci scalar, the general one, the Levi-Civita Ricci scalar. Then you have some torsional terms. The first one I will call this T, this particular combination that appears with some particular coefficients here. It's called torsion scalar. Then you have this term that, if you notice, this term is a covariant derivative with respect to the Levi-Civita. So Levi-Civita. And then it is a boundary term in an action. Plus on this is the non-metricity part, let's say. Similarly, it has a very similar structure. And I will call this non-metricity scalar, this Q. And finally, we have some cross terms between this guy. So the teleparallel condition assumes that the general curvature is zero. So this is zero. This means that the scalar as well is zero. And this is the fundamental equation, let's say, for constructing teleparallel theories. Why? Because one can formulate a theory that is exactly the same as general relativity, but instead of using curvature or the Levi-Civita curvature, we have just torsion, for example. And the reason, exactly as I said before, because the previous relationship that I show you is telling you that, for example, in the case when it's the so-called torsional teleparallel theories, so we only have torsion. Then if you put this guy to zero here, then and Q to zero, then you can have a relation between the Levi-Civita Ricci scalar and all these torsional parts. And actually this extra part is just a boundary term. So this means that if you construct the field just with T, just with this T action, you will obtain a field that is the same as GR. Similarly, you can do the same in the so-called symmetric teleparallel gravity. So when you see all of these papers on archive saying symmetric teleparallel gravity, this means that this is a field just with non-metricity, let's say, and then you can formulate general relativity just with non-metricity. So there is nothing more than non-metricity by having this action. And then in the end, these two fields are exactly the same as GR. So you don't have any different. And then you can have the so-called trinity of gravity, where you have GR, the teleparallel equivalent of GR, or the symmetric teleparallel equivalent of GR, and they are the same theory. They are the same classically. However, the actions are different. They differ by boundary terms. And then the idea is that you can construct, because okay, you have GR, okay, that's nothing important. You just have GR, the same as before. But then you ask yourself, okay, why is important? Because we can try to modify now these theories. You can go to modified teleparallel theories of gravity. And in general, modified teleparallel theories of gravity are different to the ones related to the Riemannian sector. This is one of the conclusions, and people have tried to understand these theories from these two perspectives. First, just with torsion, and then these are the so-called torsional teleparallel theories or metric teleparallel theories, and then just with non-metricity. And also you can combine the two and have some more generalized teleparallel, but this is a little bit less explored, I will say. Yeah, and then the idea is that the motivation is that you can try to modify this action, this GR, let's say, kind of action, and introduce more degrees of freedom, and see if you can get some nice phenomenology, exactly as we do in the Riemannian sector. Now we can do it in this teleparallel section. And the simplest way to do this is the so-called new general relativity. It's a very old theory from the 79. And this is just a simplest way to create this theory is just you put, instead of having this T in the action, with this very particular coefficient, you have three independent constants, C1, C2, and C3. And when these particular constants are chosen, then you just have GR, let's essentially. So this, and then when this is different, you have some modifications. So many people have tried to understand this kind of theories by using Hamilton analysis or cosmology or whatever. But in the end, the main problem of this theory is that it contains ghosts, and this is a very important problem. And the only way to avoid this is by setting the so-called one parameter new year. The only problem is that, as Costas and Jose Beltran show in this paper, this theory is strongly coupled around Minkowski, actually. So it's a little bit complicated, let's say, to bypass. So it's a little bit pathological, I will say. And then we have another branch that is called type 3 new year. That is a new branch that is healthy. I mean, the sense that there are no ghosts. This is a new branch that we just found with our colleagues this year, this paper. And this branch actually was not found before. People thought that it was not possible to find a theory without ghost by having some mixing between the so-called Carl Ramon part of this teleparallel part, the coupled with the metric, let's say. But indeed, it's possible. It's healthy from the, at least from the perturbations, and this is important to maybe to analyze further. And then the other very popular modification that maybe you also have seen a lot of papers about this in arXiv is the so-called f of t gravity. In the same idea as f of r, instead of having t in your action, you just put this as f of t. It's just a toy model of your theory. And then this was formulated just some time ago. Yeah, there are thousands of papers about this theory, mostly related to cosmology, actually. And it gives some interesting phenomenology. The only problem is that this theory is strongly coupled again against both Minkowski, Freeman-Robertson-Walker, and even non-flat Freeman-Robertson-Walker, as we show in this paper. So this means that you cannot trust perturbation theory. That's the main point. So any computation that you do in this kind of theories, both f of t gravity or in one parameter new year, you cannot do the standard perturbation theory because the modes are strongly coupled. So this means that you only have in Hamilton analysis, you have, for example, 5 degrees of freedom, but then in Minkowski, you don't see this 5, you just see 2. Even in Freeman-Robertson, okay, you only see these 2 degrees of freedom. So it's strongly coupled, and then this is a pathology of the theory. So or you can think in this way that it's difficult to work in these theories without using a standard perturbation theory. That's why this theory has been a little bit abandoned the last 3-4 years because of this issue. So from this simplest modification, we notice that it's complicated, let's say, that it works. So we need to go to a little bit further in the modification. One modification that is a little bit more general is to consider the so-called f of TV gravity. So this one is when you have like you remember this boundary term that I introduced that is related to the Ricci scalar, relating the Ricci scalar with the torsion scalar. So you can construct a theory just with these 2 guys, for example. And then, of course, you have f of r in this theory. This theory is totally free from pathologies. Of course, we know that f of r is free from pathologies. But of course, we know that f of t has this strong coupling issue. So we know that also this sector is let's say, pathological. However, we know that they have some interesting application to cosmology, like some alleviations to the H-naught tension. And we don't know if actually what is going to happen to a particular case when the theory is already related to the boundary term. This hasn't been analyzed in detail in Hamilton analysis, for example. We only know that around Minkowski, we have one extra scalar degree of freedom. So we don't know if this theory is healthy in some particular F, let's say, or some particular regimes as well. Another theory that I think is interesting to mention is this so-called Gauss-Bonnet theory. So instead of considering the standard Gauss-Bonnet G, is the Riemannian one, in teleparallel gravity, you can have 2 different boundary terms related, that they are actually boundary terms in 4 dimensions only. So they are also topologically invariant, I would say. And you can have these TGs and BG, they are different, let's say, part of the term. And then you can couple both independently in this theory. So in this theory, for example, you can have the standard Gauss-Bonnet, let's say, scalar tensor theory that is very well known and people have used it a lot for scalarization, for example. And this is what we actually studied, but not with the standard Riemannian part, but the new branch that appeared, let's say, when this is not the same as G, let's say. And then actually we found in these two series of paper that it's possible to find new kind of spontaneous scalarization process that is triggered by torsion. This is actually a little bit different from the Riemannian part. We explain this more in the second paper, but the kind of exploration is a little bit different to the Riemannian case. So I think this is also interesting route, let's say, in the teleparallel sector, because you can really have these new effects related to accelerations. And also there are more general theories, for example, this teleparallel Hordensky theory. So you construct the same idea as Hordensky gravity, the most general second order theory of gravity, but now based on this geometry, teleparallel geometry. And then in this case, if you formulate all the possible terms with some particular conditions, you find, for example, that the G phi that it was constrained in the standard Hordensky case now is not constrained anymore in this particular case. And this is what we show with Jackson and Costas and some collaborators in these two papers, for example. So I would say that these more complicated theories, these are maybe probably interesting routes to continue in this torsional teleparallel gravity. Now let's go to another part, which is the symmetric teleparallel, which is related to nonmetricity. And these theories are interested in the point of view of thermodynamics, for example, because, for example, as it was shown in this paper by Tommy, Jose, and Deborah Gomez, they show in this paper that if you, the action is different, if you start with just with the action of the symmetric teleparallel gravity, is different to the action of GR, and then, for example, you don't need to add any given your Hawking term to the action. It's just automatically there, let's say. So it's well defined, the action, let's say. And then also it's possible to define the so-called gravitational any momentum tensor. This is not possible to do in the Riemannian sector. But in this sector, in symmetric teleparallel gravity, it's really possible to define a tensor. It's a true tensor. The most modified study theory is the so-called F of Q gravity. This, of course, maybe you have seen a lot of papers about this. The problem is that, okay, this theory has 6 degrees of freedom using Hamilton analysis. We show this in this paper this year. The problem is that actually it was recently shown in this physical review letter paper that there is always a ghost in this theory. So this means that this theory is dead, let's say, because there is always a ghost. So I still don't understand why people are many papers about this every week, because this theory is let's say dead. But maybe it takes some time for people to realize that this theory is pathological, totally pathological. So, okay, the simplest part of this symmetric doesn't work, let's say. However, there is this very nice paper, a very recent paper, that show that there is a kind of K-sense theory where this particular combination of non-metricity, that this theory they show in this paper that is totally healthy, so it's totally free from ghosts, and there is no strong coupling problem. So this theory is also a new theory that deserves attention, for example, in cosmology, or I mean, any phenomenology that one wants to apply this. So yeah, of course, I didn't mention all the possible theories. There are much more. For example, we can construct the symmetric teleparallel version of Hordensky. This was done by us in this paper last year. And actually, this K-sense theory is part of this symmetric teleparallel Hordensky. So this is a subset of our symmetric teleparallel Hordensky theory. And it hasn't been so much explored, let's say, from both theoretically speaking and also from cosmological speaking. So this is also another route that people can follow, let's say, in this teleparallel setting. Okay, this is more or less what I wanted to say. It was like a brief review about the status of teleparallel theories and what I think, in my opinion, the interesting routes to go. Now let's go to a more general scenario when we have not teleparallel, so the curvature is, general curvature is there. We don't have the teleparallel condition. And then we can construct the so-called gauge formalism of Metric-Affine gravity. This is very interesting because we know that all the other forces can be written as gauge fields of gravity. And in this case, when you have all the ingredients, curvature, torsion, and non-metricity, or just the torsion and curvature, you can formulate a gauge theory of gravity based on these guys. And in the general case, you have a more general group, which is called this general linear group. Then, if you want to just have a theory just with torsion and with curvature, you have Poincaré gauge group. It's called a Poincaré gauge theory of gravity. Yeah, you have these two possible ways, let's say, formulate these gauge theories with this This is the general case when you have both torsion, nonmetricity, and curvature. So you have all of the ingredients. And then you can really define this gauge approach. Actually, this is totally dependent of the geometry. So you start from the gauge approach, you assume your symmetries, in this case, general linear group, or in the case of just torsion with the Poincaré symmetries. You do all the typical machinery or gauge approach, and then you notice that you have the field strength tensor as this. And then since you know that there is an isomorphism between tetrad and spin connection, this is a tetrad and spin connection, tetrad spin connection and metric and the affine connection, you realize that actually these two guys and also the non-metricity are related to just tetrads, let's say. And then you notice that the field strength tensor that appear in your theory are nothing more but torsion, if you have the Poincaré gauge theory, for example. And then you have the curvature as well as your gauge field strength tensor. And yeah, of course, the general case, you have as well the non-metricity, this GI here. And then you have the full gauge approach of gravity when you have the three ingredients and everything is in correspondence, let's say, with the standard gauge approach of gravity. And then how do you proceed? What you do is you only assume that your action is invariant under the gauge symmetries. For example, if you just work with torsion, you assume that your Lagrangian is invariant under Poincaré group. And then you have non-metricity, you have the general linear. And then the dynamics of your theory will be something like this. You have some matter part and some gravitational part related to curvature, torsion, and non-metricity. And then when in this formalism, usually you work with the tetrad and the spin connection, because we want to introduce a spinors, for example. And then to do this, what we do is we take variation with respect to the tetrad, and then we have some kind of energy momentum tensor. And then when we take the variation with respect to the spin connection, we have a new source here. This source is related to the intrinsic properties of matter. It's called the hypermomentum density. And when you only have torsion, this is called the spin density. And this is similar to what happened in GR. So this means that in this case, the intrinsic properties of matter gravitates. This is what is this equation saying. So this means that, for example, when you have torsion, you have extrinsic spin of any, for example, fermions, and they generate gravity. This is more or less the idea by this source called the hypermomentum. Similar to what happened in GR when you have the energy momentum tensor, when you have something with mass, energy, you have a source which is called energy momentum tensor. Here you have a new source related to intrinsic properties that are related to spin or also to non-metricity that are not so well understood, but also have some intrinsic properties. Okay. So based on this, you can construct fields of gravity with the Metric-Affine framework. And let's go to some application to this. For example, cosmological perturbations. To do this, we first need to do the standard approach for this. And when we do this, we start to do this 3+1 split. So for this, it's very useful to introduce this projector tensor like this. And then just with some properties that we have for this particular tensor that we want to introduce. And of course that if we want to decompose scalars and vectors, this is very well known. It's just this. And so in this paper, what we did was to formulate the perturbation theory of the full Metric-Affine gravity. This actually hasn't been analyzed since our paper because it's a little bit complicated and cumbersome. As you notice, you have 24 components in your torsion tensor and 40 components in your non-metricity part. And you need to decompose all torsion and non-metricity in 3+1 decomposition and then SVT decomposition, let's say, by parity. And you need to do all of these steps because now torsion and non-metricity are dynamical. So you need to really consider all of this new part. Okay, and what you do is you assume that you have some symmetries for torsion and for non-metricity. So you have, in this case, cosmological symmetries. So all the fields respect isotropy and homogeneity, sorry. And then this gives you like the metric being the standard Freeman-Robertson-Cocker, of course, this is very well known. But then the torsion tensor actually is related to two functions, so T1 and T2. And then non-metricity introduce three functions, Q1, Q2, and Q3. So you can think in this way. So the metric introduce one, let's say, a scale, one function, A of t, because you can set the lapse. But here you have 5 extra independent functions, let's say. You can think this in more like you're introducing like a vector. some vectors in your theory. And then what we need to do is we take the metric, we perturb it, we take the torsion, we perturb it, and we take nonmetricity and we perturb it. And then why this is important? Because of course any theory that is realistic must describe both background cosmology and also cosmological perturbations. And up to now, only theories, very simple theories in metric-affine gravity without kinetic terms of torsion, for example, or very, very particular theory that can be rewritten as a scalar tensor theory, have been used to explain, for example, perturbations, but not the general case that is very important. So yeah, there are only few very particular models within this, and only more focused, let's say, on background cosmology. And yeah, also the majority of these studies are mainly focused on torsion, not on metricity. Some possible things that you can do in this kind of framework is to remove some cosmological singularities by a bounce in this in the background setting. Also, that energy can be explained by some modes of torsion. And also it's interesting this Einstein-Cartan couple theory with the Higgs that is compatible, let's say, with inflation as well. But as I said before, these are very particular models, and they are not like the full, let's say, torsion and metricity. Okay, how we can do this? So first we decompose torsion as irreducible pieces in the pseudo-orthogonal group. We have one vector, one pseudo vector, and one tensor. This is the composition of torsion. And then for nonmetricity, we have a one vector that is called the bile, another vector that is this lambda. We have the one pseudo tensor that is this omega here. And finally, we have another tensor that is a totally symmetric tensor, this Q. So this is the way to decompose in irreducible pieces, let's say, these two guys. So this is very useful to do the 3+1 decomposition, because instead of consider the full T or the full Q, we can consider each piece independently, and then we are done with the 3+1 part at least. So first, of course, for vectors, we know very well how to do this. It's very simple. We just have this 3+1 decomposition. For this tensor, it has a very weird symmetry, so it's not so easy to see, but in the end you notice that you introduce one tensor, one pseudo-tensor, one vector, and one pseudo-vector. This is what you introduce, and in the end it's 16 degrees of freedom. This guy contains 16 degrees of freedom. This is just 3+1 decomposition. And then the full, let's say, perturbation without doing any parity part is something like this. It's quite involved, if you notice. Then for the non-metricity part, we have something similar. We have two vectors, simple. We have this omega part that is actually has the same symmetric properties as the previous t, small t. So it contains the same kind of objects, but with different letters. And then we have this totally symmetric part that actually introduces a new interesting part here, which is a spin 3 part, let's say, of the theory. It also introduces a new scalar and one vector. So this is like the numericity that is, of course, much more involved. So if you could decompose this in components. Okay, so now you can group all of these guys in this kind of different 3, 5, and 7 independent components. And then you notice that the 24 components of the torsion are split in this particular way. And then the most important part is this table, let's say. This table represents like the metric sector. We know very well how to compose the metric, so we know how many degrees of freedom are. We have in general 10 degrees of freedom, but then we can set some gauge redundance. But then for the torsion tensor, we have much more things, as you notice here. We have some vectors, some pseudo vectors, some vectors here, pseudo vector. And for metricity, even we have this spin 3 part. So we have a lot of new things. That's why it's extremely non-trivial to do this decomposition in not only 3+1, but now we need to go to the particular SVT because we are doing cosmological perturbations. And then we need to consider like the typical SVT decomposition, but this is like the standard way for vectors, for rank 2 tensor. And this is a new part that is not, let's say, known probably before because it's not important for other field, but it's when you have a spin free, we need to also consider a free index guy and do the SVT decomposition, and then you decompose this free index guy with a scalar, a vector, and a rank 2 tensor. That is totally traceless and transverse and traceless, like these conditions here. So this is like a standard SVT decomposition of but with this extra component, let's say. And then you notice that this is the total spectrum of torsion is much more involved. Let's say you have much more scalars, pseudoscalar vectors. You have everything, let's say, in this kind of thing. That's why it's much more complicated to do it practice. And then for numericity, you have even more things: 10 scalars, 7 vectors, for example, and one rank 3 tensor. This is a little bit interesting this way. Why is important this rank 3 tensor? Because we know that the metric doesn't have any helicity free part, so it's totally decoupled from the modes. So it's possible in a simple way to actually to do some computations. And for example, we compute a very complicated theory in our paper, and we notice that it's possible to have this spin free part of the helicity free part, let's say, of the spin free, being dynamical and having some interest in cosmology. This is something like new in our paper, let's say, and I think I haven't seen this before, this kind of spin free. And this will be interesting to analyze, let's say, what kind of effects can appear in cosmology by having this spin free part of non-metricity. Okay, this is one of the applications that I wanted to discuss today. And now let's go to some issues, okay? Because not everything is nice in this approach. There are some problems, as I before, as maybe you are aware, it's not easy to construct fields of gravity with propagating vectors that are free from ghosts. I already said some things about teleparallel field, that we have some fields with ghost, like f of q, for example. So here also, if we start with this gauge approach of gravity, in the Poincare setting, just with torsion, we have some issues in the standard so-called quadratic Poincare gauge theory. And actually, this is what I want to present here, and how to solve this problem. This is what we did this year with our collaborator, with Jorge Gigante. And the issue is the following. So if you start with the most general quadratic Poincare gauge theory, quadratic means that it's quadratic in the curvature here. So you have all the possible invariants that actually has a particular condition where when you set torsion to 0, you just have GR. This is the condition, because you can have another term here, but we neglect this term because we are just with this particular condition. And then let us just focus on the vector part of torsion. Sorry, vector part of torsion, yes, and the axial part of torsion. And then if you decompose the curvature as the Levi-Civita, the Riemannian part plus all the rest, you can write down your Riemannian part and your general Ricci part as this very complicated part. I'm just neglecting the tensor part, the T part, let's say, because we're just focusing here on the vector and axial part. And what you need to do is you need to replace these two very complicated expressions in this action. Group all the terms and do a lot of computations, a lot of algebra. And what you notice is the following. You notice that in the end, your Lagrangian can be written in this. So you have some kinetic term for torsion, for the vector part of torsion for T. Then you have a kinetic term for the axial part of torsion. And then you have some extra terms, extra couplings, like for example, this and these guys. The terms are marked with red, actually, they are pathological terms. So they actually always contains ghost in arbitrary background, let's say. So this means that we need to eliminate this term from the Lagrangian, otherwise we will have ghost. So for example, all of these terms are pathological. The only problem is that to eliminate all of these terms here, in the end, we end up with a theory that torsion is not propagating. So we only have these two extra terms here with mt square and s square that in reality is just mass terms for torsion. So this means that we have a problem here. If you start with the Poincare gauge theory and you start with the standard quadratic theory, we cannot have a theory with propagating torsion terms. It's always unstable. This is one important result about this. Yeah, people thought that this is not possible to cure, and it was kind of a problem, let's say. But then people didn't realize that actually when we say quadratic in curvature. But if you notice here, this is not quadratic anymore in all the fields. You notice here that you have some instant tensor coupled to the vector. So this is already cubic, if you think about this. So it's cubic in all the fields. Even this guy here is quartic, let's say, because you have 4 times there, some interactions. So when we say quadratic, a standard quadratic theory is quadratic in curvature, but it's even cubic or even quartic in all the fields. So it's very natural actually to think that the truncation done by this quadratic gravity is not correct. And then you need to go further and consider cubic parity preserving parts. So this means that you need to consider all possible cubic interactions and add these terms to the quadratic part. So for example, the first part is the simplest. You just have the Ricci coupled with the torsion, with the vector part of torsion, and then the same with the axial and blah, blah, blah. All the possible terms, and in the end are 26 terms. This was discussed in this paper. If you do the same computation again, you analyze just the vector and axial part, and then all these pathological terms in red here can be actually cancelled in a non-trivial way, like these particular combinations. And if you do this, in the end, you end up with a theory with torsion, propagating torsion, while the vector part and axial part of torsion are totally free from go. So it is possible to cure the problem, let's say that we have in the quadratic sector. With these particular conditions, of course, this is not enough because we also need to prove what happened in the tensor part, but at least the known stabilities in these theories are related to the vector part and axial part. So this is the very important, let's say, conclusion that you need to add cubic interactions to really to construct a stable theory with propagating torsion in the gauge formalism. This is very important to say. Gauge formalism, of course, if you forget about gauge formalism, if you say, okay, I want to construct a theory without the gauge formalism, you can do whatever you want. You can put any term in your Lagrangian, but I think the gauge formalism is very nice, let's say, motivated. And that's why it's important to, because only some particular scalars are possible in this approach. Only the ones that are related to Poincare symmetries in this case. Okay, so now let's go to the general metric-affine gravity. The general metric-affine gravity, again, and concentrate on the vector part and the axial part of these two quantities. So the blue parts, I will not concentrate on the tensor part again. And let's try to see what happens if we introduce non-metricity in this more general case. So now we have two extra vectors, as I said, this W and this lambda, let's say. And then before it has been shown that it's possible to have non-metricity propagating in the quadratic sector, in the quadratic theory. But of course, as I said before, torsion cannot be propagating. So this was like the conclusion that we had before. Only non-metricity can be propagating to have the correct, let's say, non-pathological terms. So the question here is it possible to have now both torsion and non-metricity propagating in a stable theory? This is the question that we wanted to address here. This is a paper that it will be submitted soon in arXiv, like probably in 2 more weeks. And the same idea as we had before, but now it's much more involved. So you want to include cubic interactions again. We consider the quadratic part plus the possible interactions. And then you have much more things to do. For example, you have this curvature torsional term. And this part, you have much more term than before because now the curvature tensor has less symmetries. So instead of 26 terms, you can construct much more terms. The same for this curvature non-metricity parts. Now you can start having couplings like this, for example, like this kind of couplings. And also you have a lot of terms. I don't remember how many, but there are many terms. And then the most involved part is actually the part that you can have interaction between torsion, non-metricity, and the curvature. This is also a cubic term. And for example, this kind of term here. And if you combine all of this together, you can have the so-called cubic metric-affine gravity. And then the idea is similar to what we did before. I am not going to show this because it's extremely complicated, but the point is that you do the same, you decompose everything in a post-Riemannian expansion, you try to eliminate all the possible pathological terms that we know that they are pathological. We analyze the kinetic matrix to have always non-negative eigenvalues in your metric-affine gravity. And then the conclusion is the following, that by adding cubic interaction, it's also possible to construct a stable theory with both torsion and with non-metricity in the gauge formalism. So let's say that this paper finished this idea, and now we are, let's say, fine in this framework. Now the idea is to understand better the tensor part of this problem. Now let's try to okay, this is more or less one application that we found in this paper as well. This new paper is about spherical solutions. So if you assume a spherical symmetry in all the fields, similar to what we did before in cosmology, then you have 8 degrees of freedom in the torsional part and 12 degrees of freedom in non-metricity, plus the 2 standard degrees of freedom for the metric. We put this in our theory that is extremely complicated, but then you solve for torsion, non-metricity, for the connection equation, and then you go to the metric equation and you solve for phi 1 and phi 2. After doing all of this very complicated computation that I will not go into show, it's possible to find that a solution that is a Reines-Nostrom-like black hole solution, and is actually in the ghost-free theory. It contains three charges. These three charges are related to intrinsic spin, so related to torsion, and intrinsic dilation that is related to the bile part of non-metricity, and intrinsic shear, and they are related to intrinsic properties of matter now being dynamical and appearing in the metric. Important to say that we already in some previous paper we found something similar, a similar solution, but we had a problem in those papers because it is very well known that if you have a spin 2 and spin 3 propagating, they need to be massive, otherwise you have some problem in the quantum regime. But in this case, actually it's very interesting to notice that the only solution that you find is always with a massive spin 2 and spin 3. So we automatically evaded the Weinberg-Witten no-go theorem. So this is very nice because without assuming anything, let's say actually, automatically you arrive by this very nice result, let's say. Okay, I don't have so much time, so this is another application that we did. Maybe I will just very briefly mention. So what we did was this since it's very complicated to work in this Metric-Affine gravity, we need to understand symmetries. How are symmetries in these theories? And the best known way to do this is the so-called algebraic classification that is very well known in mathematics and in the Riemannian sector. And this, for example, has been done for the curvature tensor in the Riemannian sector. And this is the way that you do it. You first decompose the curvature in the bile part, the Ricci part, let's say, that is traceless, and then some Ricci scalar. And then this is 10, 9, and 1 degree of freedom. So in the end, you have the 20 degrees of freedom. And then you do the so-called algebraic classification based on either the eigenvalue or problem of this tensor, or by using the principal node directions. And this is a so-called Petrov classification for the bile tensor. This is very important in GR. And then the so-called Segre classification for the Ricci traceless. And yeah, in GR, we have this particular case always when we have this 6 type of the bile tensor. And in GR is quite simple in vacuum. Yeah, this is a little bit technical. Okay, what you do is you introduce these null vectors, and then you classify with different mathematical criteria how this tensor is aligned to these particular null vectors. And this is so-called Petrov classification. For example, the most important one is this called type D. Type D kind of classification when you have this particular condition for your bile tensor. And this type D is important because why? Why do we want to use this? Because first of all, even Einstein's field equations are very difficult to solve because they are non-linear partial differential equations, and they are very complicated to solve. So we need certain symmetries, and to understand this, to obtain exact solutions, we need certain approach. And for example, actually, Kerr Newman was actually found uses these ideas in the 60s, and actually it was found that it's a type D type of solution. And this is very important from mathematics physics point of view, because not only the curvature is type D, but also the Faraday tensor, like Kerr Newman, also fulfill this property. And it has some particular theorems, like mathematical theorem related to geodesic, shear-free null geodesic congruence in GR. So it's a very important, let's say, property of general relativity. That's why we say, okay, now we have this very complicated system with more degrees of freedom, torsion, or metricity. Now we need to understand this better by classifying this tensor algebraically. I don't have the time to do this so quickly, but the idea is done in this first paper, first of all, where we separate the curvature, general curvature now in the antisymmetric part and symmetric part, and then you have all of these independent components, all of these building blocks, let's say. You notice here that you have some kind of bile tensor, but it's a generalized bile tensor. You also have some Ricci traceless. So you have something similar to the Riemannian case, but you have more. For example, this guy contains 30 degrees of freedom that is related to non-metricity. And then, yeah, you can group this kind of guys by their symmetries, and then you can classify them. You can see the details in our paper. And then in the also in the our last paper that we did the most general case, the Metric-Affine gravity, where we have the richest part of this model, which is this zeta 1 that contains 30 degrees of freedom with these particular properties. And as we shown in this paper that we published, we put like 2 weeks ago, more or less, that using this principal node direction, we found that this tensor can have 15 main types. So not much more complicated than the Petrov classification. And not only that, we also have a lot of subtypes. So this was a very complicated let's say exercise. But then we noticed something very interesting, that for the spherically symmetric solution that we have in our previous paper, we have a Black-Scholes solution, and though with shears, it's called shears charge, we found that actually even in a spherical symmetry, this guy is not longer a type D. So this, I think, we haven't seen any situation where we actually in a spherical symmetry, there is a solution that is not type D. And actually we have this in our theory. So being dynamical, let's say. So I think this is also showing that this is very rich, let's say, this kind of zeta 1. Yeah, okay, so I think that, okay, I only have some minutes, so I don't know if I can do this, but let's briefly summarize. So I talk about different things. First of all, I talk about the so-called teleparallel theories of gravity, where curvature vanishes. And in this case, you can formulate these theories from torsion only, from nonmetricity only. Also, you can combine them, but this is like the standard way of doing this. And then you can modify these theories and then construct new theories of gravity that are, I will say, richer than the Riemannian theories. Why they are richer? Because it's always possible to formulate the teleparallel theories as a Riemannian part plus the teleparallel part. And this teleparallel part, let's say, is new. So you can always put this teleparallel part to 0, and you will recover the Riemannian part, as I said, for example, in f of TV gravity, that you can always get f of r, or in the Hordensky, teleparallel Hordensky, that you can always get the standard Hordensky. But you have more, you can have much more things. So it's richer, I will say. The only problem is, okay, the simplest theories have a lot of pathologies, although still there are some room by some theories that I mentioned here. But the most complicated theory must be analyzed, let's say. Like the theories that I already discussed here. Finally, okay, the part that also is interesting is this gauge approach to gravity, when you have everything like torsion, nonmetricity, and the curvature, and they appear as a field strength tensor of a particular group, which is called the general linear group. And then we constructed under this very complicated case the perturbations of this. So SVT decomposition, 3+1 decomposition, and then SVT. And then we noticed that torsion and nonmetricity, they have a lot of new species, a lot of vectors, pseudo-vector, tensor, even spin-3 parts appearing and can be propagating. Also, in this presentation, I show that it's possible to cure these instabilities known in the so-called quadratic Poincare gauge gravity, just by introducing these quite reasonable cubic interactions. And then even in the Metric-Affine gravity, it's possible to do this. So it's possible to have both torsion and nonmetricity propagating without instabilities. And then we found this very nice Reinstein-Nostrel-like solution that with dynamical torsion and nonmetricity, when these new charges are associated to intrinsic properties of matter. And then we evaded the known problems of massless higher spin particles, because in our solution we have masses for torsion and nonmetricity, for the spin 2 and spin 3 specifically, that they are dynamical. And yeah, as I said before as well, it's very difficult to work on this theory. So in parallel, we work with this Petrov modification, this classification of our curvature tensor using the same idea as the algebraic classification. And we did this in 2 series of paper, first for the Bike-Cartan and then for the general Metric-Affine gravity. Okay, and what to do next? So there are many things that we can do actually. First of all, is we can try to study this new branch that we just found this year in new general relativity, the torsional version of teleparallel gravity, that we know now is free from ghosts. Is it really strongly coupled or not? We believe that actually it's not strongly coupled, but then is it or not interesting, like from, for example, cosmology, or I don't know, black hole physics? And then investigate the stability of the tensor sector is important in both Poincare and Metric-Affine gravity theories. We didn't analyze the T, it's very important to say that this analysis that we did is totally arbitrary, in arbitrary backgrounds. It's not affected by the background. And then, yeah, for example, torsion nonmetricity can, for example, these new fields alleviate tensions in cosmology in a natural way with the gauge approach, for example. Also, it can be important to study axial symmetry in these scenarios because we expect to have some kind of interaction between the intrinsic spin and the macroscopic spin, J and let's say kappa sub S in our theory. And this actually will be very similar to the so-called spin orbit interaction that is known in physics, that has been measured. But this will be the gravitational spin orbit interaction. This is very interesting as well, that can appear in our theories. Also, is it possible to find a renormalizable theory with this cubic interaction? This is also not known. And yeah, because we know very well that the quadratic sector contains ghost. Even in the Riemannian sector, we have quadratic gravity that contains ghost. But we don't know if this cubic part may alleviate because of these new interactions, may alleviate this problem, and maybe one can find a renormalizable theory without ghost. And yeah, this is more or less what I wanted to say today. So I think I took a lot of time. So thank you very much for listening. And yeah, I'm happy to discuss any of this.
Thank you very much, Sebastian, for the nice overview of metric-affine theories. Yeah, are there any questions from the audience? There is some inertia.
I have one question.
Sure.
So first of all, thank you, Sebastian, for the talk. So when you mention the intrinsic property of, for example, nonmetricity, so are you referring to, for example, the dilation or shear that appear in your rest-neutron charge, or could it be something else?
Yeah, the point is that, okay, as I said before, in metric-affine gravity, dipole momentum, you can split dipole momentum in 3 pieces. The first piece is called the spin part of dipole momentum, and this part is only related to torsion, is the symmetric part. And then this is just related to the group of you can always separate the group of the affine group in the Poincaré, semi-plot of a Poincaré, and the bile part is related to the dilation group, and then you have the shear. So these 3 parts, let's say, are split, let's say, in this dipole momentum, and they represent like different properties intrinsically from the matter. So the dilation part, let's say, actually in nature, we haven't detected yet something like a particle with dilation, for example, or with shears. But we expect that maybe this kind of new parts might be relevant in some quantum regime, for example. This is not known. The part, of course, that is known is the intrinsic spin. This, of course, this has been measured. But these theories predict that this intrinsic spin generates gravity. So you need to think that this dilation, the same, is a particular property of matter that is related to a group of dilations, in this case. And this, if you think in a theory of particle, like a standard model of particle physics more general, you may think that also particles will have their own dilation and shears, and they also will generate gravity, something like that.
Somehow I guess this may require, like, we need to go beyond standard model of matter fields, right?
You need to go beyond to have exactly to predict that particles also have dilations and shears. And actually that part of metric-affine gravity have not been so well studied. And I will say that even this, I mean, the shears part, for example, they are okay. The mathematics is it's easy to understand, let's say, but I will say the physical interpretation is difficult. This is still people need to understand this better. And in my opinion, there are some people from the 80s, from the 90s, from very good people claiming that this kind of group that you need to formulate a bigger group than the standard model particle physics will be important for quantum gravity theories. So this is the main motivation.
Thank you.
Welcome.
Any other questions? There was a question in the chat about where you can find the recording and the slides. This will be uploaded in the website that I attached. So yeah, any other questions regarding the talk? I have a question actually. So I want to ask about the perturbations that you showed. So I think you showed at some point that you perturbed the metric, the torsion, and the nonmetricity, and all the rest of the analysis was based on the degrees of freedom of the metric, the torsion, and the nonmetricity. But like the fundamental objects of the theory, like the geometrical objects, are the metric and the connection, actually, right? I mean, these are the ones that you perturb. You don't perturb the torsion itself or the nonmetricity itself, right? You perturb, I mean, these are derivatives with respect to.
Yeah, okay. What you, of course, both formulas are totally equivalent. If you take the perturbation of the full connection, let's say, you put connection plus delta connection, and then you separate the connection into, let's say, all the pieces, you will obtain exactly the same spectrum, let's say. But we thought, we have actually some thought about this in this paper as well, that is much more natural to consider the pieces, let's say, the torsional part, which is like the building block of the theory, which is the torsional part and the metricity part. And then you really see the part that is like physical, because you see, okay, for example, torsion, you can notice that you have the scalar part of torsion, and then you have the vector part of torsion. So it's much more natural to consider like the connection, but of course it's totally equivalent because it's a completely equivalent description in the end.
But then why not consider the curvature as well and you consider the metric?
No, it's different because you can always, what is in the Metric-Affine gravity, you have the metric, torsion, and nonmetricity are the new degrees of freedom, or equivalently, the metric and the connection. The curvature always you can write it down as a decomposition, because the curvature always can be split in the Riemannian part plus torsion or nonmetricity terms. So the curvature is not, you don't need to perturb because automatically depends on torsion and nonmetricity. That's the reason. There is no need to do it with the curvature. It's just the new degrees of freedom are always encoded in torsion, nonmetricity, and
but
then
the torsion can be also decomposed in terms of connection, and the nonmetricity can be decomposed in terms of the metric and the connection. So
but the new degrees of freedom, these 24 degrees of freedom of torsion, they are fully independent of the metric. So you have it's not like in teleparallel. In teleparallel, you constrain your theory and then you only have a Carl Ramon, let's say, and then you have 6 degrees of freedom. But in the Metric-Affine gravity case, you have the 24 components of the torsion tensor. It's a full torsion tensor. So it's a tensor that is a totally new part, new degrees of freedom. And the same with nonmetricity, that is 40 degrees of freedom. So in the end, the curvature tensor is just in the end, is a manifestation of the torsion part and the nonmetricity part by the post-Riemannian expansion. So in the end, everything can be built by metric, torsion, and nonmetricity, or equivalently metric and the affine connection, general affine connection. These two approaches are equivalent, but we thought that it's much more appealing and physical to consider the perturbation of torsion and nonmetricity, because you really see how are really the species of them appearing. I mean, like this.
No, I totally agree, of course. Yes. Yeah. Good. Okay. Thank you. Yeah. Any other questions? Or maybe I should turn off the recording because. Okay, let me close it here.